Okay, so this section we're going to talk about nuclear chemistry, and we're going to look at what happens to the nucleus when certain particles are being emitted or certain energy is given off. And in this section here, we're looking at a source, and it happens to be radioactive. And we'll talk about next week why it actually has lead surrounding it. But notice that there's 3 types of radioactivity that can come from a radioactive sample. Alpha, beta, and gamma are the 3 possible types. And notice that the first type is actually the size of a helium nucleus. Now this is a positively charged particle. So it's the same size as a helium nucleus. And because it's positively charged, it's actually attracted to a negative plate or a negative field. Now beta, which is the size of an electron, so it's significantly smaller, it is negatively charged. So because it is negatively charged, it would be attracted to a positive plate or a positive field. And notice that it's actually bending more than the alpha particle, and the reason why is it's a lighter particle. So because it's less mass, it moves significantly more or faster because of that. So a helium nucleus is heavier, and because it's heavier, it bends less towards a negative plate. Now the important thing to remember is gamma is radiation. It has no mass. So because it has no mass, it can't have any charge, and as a result of it, it is not affected the way alpha and beta particles are affected. Okay, so we're going to look at radioactivity reactions, and please remember that there's a difference between beta and alpha emission. So when we're talking about alpha, we actually see a decrease in atomic number. So the element that is shedding alpha particles actually goes down by 2 atomic numbers. The opposite happens with an isotope that sheds a beta particle. It actually increases its atomic number. And I know it probably seems strange, but when you see the actual reactions, it'll make sense. The most important thing to remember is that these isotopes actually become different elements when they release these particles, and that's something we need to keep in mind when we're talking about this. Okay, so here I have some quick notes about the structure of the atom. So notice that at the very top here, 197, for that isotope, by the way, this is an example of isotopic notation. Notice that the mass number is a combination of the protons and the neutrons. And the bottom number is the example of the atomic number, and that's the protons. Now, please remember that if we're talking about a neutral isotope, so it's not charged, we're assuming that the number of protons will equal the number of electrons. Now, if you do have a charge, that probably means that you have more or less electrons, and we'll talk about that eventually. Okay, so here is a radioactive reaction here, and we have to follow the law of conservation of mass. So the universe does not give us a free lunch, so we have to make sure that we follow conservation of mass. And what does that mean? That means the mass of the reactants has to equal the mass of the product. So for any of these reactions, you have to make sure that both masses on either side are equal to each other. So this is how I would approach this. Please remember, this is alpha decay because we have a helium nucleus. And we are going to essentially add up the product masses. And when we do that, we get 238. And notice that on the left-hand side, that is the mass number of uranium. Now we want to do the same thing with the atomic number. And notice that 90 plus 2 gives us 92. And that is the atomic number for uranium. Okay, so we're going to do a beta decay here. And the important thing to remember is when you see a -1, that is a sign that we're talking about a beta particle. And please remember, we said that the atomic number would increase. And how do we figure that out? Well, once again, follow the law of conservation of mass. And when we add 40 plus 0, we get 40. So notice that mass does not change. So with beta decay, mass typically does not change. So the mass number. However, the atomic number does, and we said that it increases. And this is why it increases. So if we have 20 plus a -1, doesn't that equal 19? So that is the reason behind why we see an increase in atomic number. Okay, so here are 3 modes of beta particles. The first one here is beta decay. And the reason why we know it's beta decay is because of this -1. And we also see an increase in the atomic number. Now the second reaction here is actually electron capture. And the reason why we know that it's electron capture is on the left-hand side of the arrow, we see it almost looks like a beta particle. And the difference here is that the atomic number decreases. So with electron capture, the atomic number goes down. So that's the difference between beta decay. So beta decay atomic numbers go up, but in electron capture, the atomic number goes down. Now the H nu that you see, that is actually X-rays. So X-rays are emitted with electron capture. Now this last one here is actually positron emission. And notice that the atomic number goes down. So it is not a beta decay because the atomic number goes down. Okay, here is gamma emission. Now, gamma emission sometimes is a little trickier to figure out. Typically, I look for no change in mass. So this bottom reaction here has no change in mass. And I know that beta decay also has no change in mass. The other thing is when you see a gamma emission, you also have no change in atomic number. So gamma emission, typically you do not see no change in atomic number. Now this top one here, so they're showing you beta decay. So this is beta decay. So notice it's beta decay because the atomic number goes up. So when beta decay occurs, we have atomic number increase. But in the bottom reaction here, we have no change in mass, no change in atomic number. Okay, here is an example of fission. Here we have a very large nucleus. 252 is pretty high, californium. And it actually splits not quite evenly into 2 separate elements. And here is a neutrino as a result of it. Now the interesting thing is that scientists saw that there was a trend when it came to radioactivity. So notice that you have this line here, and it's neutrons over protons. And that means that the number of neutrons is pretty close to 1 with the protons. So it's a 1-to-1 relationship. And they give you an example here like with neon. So when you notice that the number of protons is starting to exceed the number of, So this line here is when the number of neutrons is actually higher than protons. This is where you have a shift in stability. And typically iron is the breaking point of where we see a shift in stability. Okay, so any nucleus that is above the ratio of 1 is considered neutron-rich. And then any element that is lacking neutrons is considered neutron-poor. When you start veering from that zone of stability, that is where you get radioactivity. So radioactivity is really hinging on the number of nuclei. And it makes sense because we know that the protons are positively charged and the neutrons are good at spacing out those protons so that we don't get so much repulsion. But the moment we start adding too many neutrons, that balance has been shifted, and as a result, the nucleus is very unstable. Okay, so here's an example of a neutron-rich versus a neutron-poor nuclei. So notice that U-238, its ratio is neutron-poor. So on the left-hand side, this is an example of neutron-poor nucleus. And as a result of it, it cannot hold on to all of those neutrons and some of the protons. So as a result, it releases a alpha particle. Okay, so here I'm just going to briefly go through this. I'm going to show you a second video of how to actually do these calculations. This was the reason why Einstein was very concerned during World War II. He was really worried about the access that the Germans and the enemy forces had when it came to nuclear energy or nuclear power. So, and it's all because of this equation here, E equals mc squared. And scientists were starting to figure out that if you add up all the neutrons and protons, you should have a certain mass. Well, they were finding that these heavier nuclei actually had missing mass. So they were thinking this mass had to go somewhere. And Einstein was very good at finding out the relationship, which is energy is equal to the mass times the speed of light. And the reason why he was concerned is the fact that elements were able to convert that missing mass into energy, which holds the nucleus together. He was afraid that scientists on the enemy side were going to be able to harvest and use this energy into unfortunate purposes. So notice that binding energy per nucleon equals binding energy over mass number. And like I said, I will give you a second video where I show you how to do that calculation. Now the interesting thing is, and this is a very good graph to help us understand what's going on. So I mentioned to you about that zone of stability. So iron is one of those interesting nuclei that it's in that sweet spot where it has the right ratio of neutrons to protons. So it's a very stable atom, and anything that's before that element actually can undergo fusion. So here they show you this, it's almost like a hill that the elements are trying to come up towards. This actually happens in stars, by the way. So every star has the opportunity to start with hydrogen. Hydrogen is just a natural resource that is found infinitely, well, not infinitely, but it's found in a lot of different places throughout the universe. And eventually enough mass of hydrogen gets together to start to create these stars. And these stars, they are able to fuse all these different elements up through iron. So iron is the final element that actually stars are able to form within their core. And you're probably like, well, where are the other elements coming from? The other elements are either man-made, or a good chunk of them are made through supernovas. So when you look at the elements that are found after iron in the periodic table, those are all elements that have been created by earlier stars that underwent supernovas. Now, if you look on the right-hand side of the equation here, notice that all of these elements, and depending on what the atomic mass is, because their ratio is not close to the zone of stability, they are more likely to undergo fission, and they keep undergoing fission until they approach iron. Iron is pretty much the stable sweet spot that nuclei have. So you can kind of predict what's going to happen to the elements when you combine them. So obviously if you try to combine heavier ones or even a smaller one with a very large one, you're going to undergo fission. If you have two smaller ones that are under iron size, you probably are going to have fusion. Okay, and here is just a couple of example calculations where notice that we have californium, which has a huge number of nuclei, and as a result of it, because it doesn't fall within that zone of stability, it's undergoing fission. Or you could have the opposite situation where you have two carbon-12 isotopes that are small enough and stable enough to fuse together. Okay, so I'm going to pause here and I will come back to kinetics next week.